Okay, I'm going to be starting recording some Zoom lectures, just audio over the slides. I'm going to try to keep these to about 15 minutes as much as possible, so that you can easily download them and watch them. As I said, I will be putting these up probably as YouTube links that you can then link to from the Campus Blackboard page. So I'm just going to start all over with the chapter that we began before spring break, because I don't exactly remember where we stopped. And anyway, it's always good to review. So it is 10:09 right now. Hopefully by 10:19 or so, I will have a short segment that I'll be able to talk to you about that I will try posting. So this chapter of soils is going to be clays and colloidal particles. And of course, this is chapter 8 from your textbook. There are some YouTube links in here that you can go and watch on your own. All of that, there's the YouTube link to the Brownian motion. But just to review, I know I've covered this before. Colloids are extremely small particles. We consider clay to be any soil particle of mineral origin that's less than 0.002 millimeters. That equals out to be 2 micrometers, because a micrometer is 1/1,000,000th of a meter. A millimeter is 1,000th of a meter. And they can be much smaller than this. They're also sometimes referred to by the term micelles. So you see micelle sometimes used for clay particles. And a lot of these, the only way we have of visualizing them is usually with scanning electron microscopy. So in your textbook, and then also in these lectures, there are some micrographs that have been taken with SEMs of clay particles. And it's kind of cool because you can see the very fine detail of these, which would be absolutely invisible to us. And as I said, they do show Brownian motion, which means they will collide with water molecules. And as a result, they will then vibrate. Some more characteristics of colloids. The big thing about it is the smaller an object is, the higher the ratio of surface area to volume that it has. Additionally, with clay particles, remember, unlike sand and silt, which are more or less cuboidal in shape, clay particles have a flat, platey shape, and they have a very small volume relative to their surface area. If you have your textbook with you, you can look at figure 8.1 in your textbook. In a moment, I will have some images that will kind of take the place of that if you don't have your textbook. Generally, because of the mineral structure of clays, they have something that is known as isomorphic substitution. I'll talk more about this later on. This substitution gives them an electronegative charge. And so in a lot of ways, they behave more or less as giant anions. And as a result, they attract swarms of cations to their surface. As a result, these cations attach to the surface of the clay particle. This is called adsorption. Notice the AD, adsorption. And this provides nutrient availability for plants. They're also able to hold water. Now, some of these characteristics of clays, of mineral clays, also apply to certain organic compounds, like humus, like some other forms of organic matter. So the ability to hold cations, the ability to hold water, the electronegative charge, more or less, all of those are also characteristics of organic matter in soil. This is the link here for the Brownian motion demonstration. I know I showed that in class. Here are some of the images of clays. And one thing you can notice, particularly on the kaolinite right here, and I'm kind of moving the cursor over it, you can see that it looks like a series of stacked flat plates. And the shapes of the clays, to a certain extent, represent their crystalline structure. Ecology, the mineralogy of crystalline structures is really very interesting. It's something way beyond the scope of this class, but something that a person could probably spend an entire career studying. But clays do have various types of structures to them, some of them having a very regular crystalline structure, some of them having a more amorphous or irregular type of structure. So some of the functions of these in the soil, they have a major influence on soil texture. Even a relatively small amount of clay in a soil has a big effect on the texture of the soil. And if you go back and if you look at the texture triangle, you will see that clay plays a major role in influencing soil texture. They're also very important for water holding capacity. Clay tends to attract and hold water. And in fact, some of the industrial and other uses of clays actually draw upon that water attracting property. It used to be, I don't know whether it's still composed this way, but kaopectate, which was an anti-diarrheal drug, used to contain kaolin clay. That's where the name kao in the kaopectate came from, because that clay would draw water to it and would help reduce the amount of water in the digestive tract, which then would slow the effects of the diarrhea. Similar things in soil. Also, that sort of binding property is why clays are sometimes used to bind inks to paper, for example. Clays also hold nutrients in soil, particularly cationic nutrients. This would be calcium, potassium, magnesium, those sorts of things. So the cation exchange capacity is the ability of a soil to hold and then release cations into the soil solution. And the cation exchange capacity of a soil is largely dependent on the type and on the amount of colloidal particles that are present. So cation exchange capacity, this is something that can be measured. This is the pattern of adsorption of ions to soil colloids. And then it's also possible that these ions can be displaced by other ions. In some cases, by one that would be held more tightly. In other cases, just by an excess of them. One of the things plants do to get nutrients out of the soil is they will release large amounts of acidic material into the soil, and that hydrogen ion, H+, in the acid they release, will knock off certain nutrients from the surface of clay particles. Those nutrients then will go into the soil water solution, and the plant can take them up with its roots when it takes up the water. Cation exchange capacity is also influenced by leaching. Rainwater, as water falls through the atmosphere, it interacts with the naturally occurring carbon dioxide in the atmosphere. This forms something called carbonic acid, which is a weak acid. From your chemistry class, remember, a weak acid is one that doesn't totally dissociate. So there will be some carbonic acid, some carbonate ion, and some hydrogen ion in the rain. Typical rainwater, even in non-acid rain conditions, is going to have a mildly acidic pH. This is why rainwater is sometimes referred to as soft water. This is why back when my grandmother was a girl, growing up on a farm, they used to collect rainwater in rain barrels to wash their hair and to wash linens with, because the groundwater that they got from the well had dissolved calcium and other substances. That hard water, that well water, made it much more difficult to rinse soap out of things. And so you washed your hair with the mildly acidic rainwater because it was easier to get the soap out of it. A similar thing people do these days, and I do it sometimes, you put a little bit of vinegar in the final rinse when you're rinsing your hair. Don't get it in your eyes, obviously, but that will do a similar thing, and it actually does make your hair a little bit softer. So that's just sort of a fun fact there from that. So carbonic acid is a reaction product between water and carbon dioxide. You may have in past years in grade school science classes seen the trick where you have water that has lime dissolved in it and you blow into the water with a straw and it turns cloudy. That's essentially a reaction precipitating out a carbonate because of the carbonic acid from the carbon dioxide in your breath reacting with the water. I already talked about plant uptake of nutrients. This is also a way in which hydrogen ion is important. So cation exchange capacity is measured in units of centimoles. Remember from chemistry, a mole is a measure of concentration. So it's measuring the concentration of positive charge per kilogram of soil. So essentially what this is this is the sum total of exchangeable cations that a soil can absorb. And it depends on the charge of a cation. You can either get one divalent like calcium that is Ca2+, or two univalent like potassium. So one calcium, which has a charge of +2, or two potassium that each have a charge of +1. It's sort of an additive thing. So in temperate regions, like where we live, the most common ones are calcium, aluminum, and hydrogen ion. In tropical regions, you get a little bit of difference because of differences in the age of the soil and weathering rate. You tend to have more sodium, you tend to have more magnesium, and you tend not to see the hydrogen ion as much. Also, different cations are held with differing strengths. Here they are. Lithium is the most weakly held. That's going to be on the far right-hand side, working the way up to aluminum, which is the most tightly held. And this actually kind of paves the way, which I will talk about in the next short lecture, about how you can measure the cation exchange capacity of a soil. So I'm going to stop recording now. I'm going to try uploading this and see how